Okay, well, welcome to everyone. The theme of this talk really could be summarized in a couple of comments. I'm always interested in anatomy, really from the angle of how does the hand dialogue with the world, and how does its anatomy enable it to do so? That's really going to be running through this talk. How do I move on? Oh, okay. It's arguable that sight is our most precious sense. It's by far the most important. Incidentally, when I use the word important throughout this talk, I mean, if you lose it, how bad is the functional loss? Of course, everything's important. But so the eyes are probably our most precious sense, but the fingertips come quite close with the gathering of information. The advantage that the hand has over the eye is that the hand can also act on what it sees, on the information it's gathering. And as a result of this, the hand has shaped everything around us. It is our main mode of interacting with the world, apart from speech, in any profession. And it's immensely versatile, capable of great strength and great accuracy, whatever the profession, including most of those who are listening to this talk now, and also in order to provide us with food and domestic activity. And the hand has quite literally built the world we see around us and the world we inhabit, from humble to grand dwellings. Even a brick is the dimensions it is because of the size of the hand, for it to be easily handled and therefore more versatile. And so, as we shall see throughout this talk, there is an enormous spectrum of activity that the hand can follow, and the anatomy, which is relatively simple, is adapted to allow it to achieve all of these things. So the first concept really is the hand as a communicator, the language of the hand. Most Latins will use their hand somewhat more than others, and hands are very expressive, as you can see here. And not only that, but we are programmed to watch the hands and to have them reinforce or emphasize what the face is saying. So for example, in this pair of individuals, the position of the hand and arms is identical, but the message being conveyed is entirely different, as you can see. We use our hands to comfort others. There's a great sense of empathy when hands hold other hands. Of course, considering the hand as a communicator, there is a formal language to hand. There is sign language, but there are also other more subtle forms of sign language in particular spheres. For example, in the music sphere, any musician that's sitting in this orchestra watching this man can tell what he or he is saying and obey orders. Culturally, we also adapted to take a message from postures of hands. Nobody doubts what these hands are doing in this engraving by Dürer. And this is probably an international signal. We do know what this woman is trying to tell us. Of course, in different cultures, the same sign may mean different things. So one needs to be careful. The hand also has a choreography. When we look at hands like these, for instance, most of us can work out how this hand is going to behave, how those fingers are going to dance. And you only have to see them then spring into action to see what could have been predicted from that first drawing, that the thumb was going to buckle unstably, in an unstable way. Remember also that the hand is the only part of the anatomy that it is permissible to touch in polite society. Even opera royalty, here's Maria Callas in 1973 in Paris giving one of her many farewell concerts, and her adoring fans were allowed to touch her hands. And of course, one needn't go far. You're only allowed to touch the Queen's hand and nothing else. The back of the hand is a very important aesthetic unit, virtually as important as the face. In fact, it's always exposed. always visible to those who are in contact or within distance, even in cultures that cover their faces. And so it's a very important concept to keep in mind whenever you're putting a scar on the back of the hand. In the hand, function and aesthetics are the same thing. So the hand that behaves in a fluid and natural way, for example, like this hand, tends not to attract attention because most people will see function and will therefore not count the fingers. They will not notice, most people will not notice that this hand is missing one finger. In fact, one could stretch the point and say that if the finger is present but abnormal, it's going to attract more attention. This is not a recommendation for amputation, but you get my point. But the more interesting language, these are all very obvious expressions and communication of the hand, but the more interesting language is that of performance. And that's really what this talk is about. How does the hand speak by its performance? And when you see normal hands in action, particularly performing dexterous activities like this, I like the concept that this hand is eloquent. And this hand, for example, has a rich vocabulary. It's a very useful concept, and it actually rather defines what we do. We add vocabulary and eloquence to hands like these, which are ineloquent. Particular professions, of course, have a special place for the hand. Musicians not only earn their living with their hands, most of them, but their identity as musicians is rather tied up in what their hands are doing. In fact, sometimes you see photos of pianists like Lang Lang who almost fetishize their hands. He seems to include it in almost every photo, include his hands. And this is a posture which is almost artificial, as you can see. It's a very posed attitude for the hands to take. The second big world is, of course, that of sport. Those of you who treat professional sportsmen will know how much is invested in the performance of the hand and how much store is put by its, for example, recovery not being too delayed. Those of you who treat professional rugby players, for example, will know how difficult it is to keep them off the training ground. And there are some sports, of course, where the hand is actually, the performance of the hand is a matter of life and death. One depends on that hand not letting the person down. But of course, in daily life, there is what I call a versatile strength to the hand. It would be difficult to imagine a strong machine that could perform what these hands are doing. It could perform it more powerfully, but not as dexterously or as in such a versatile manner. And then, of course, one need only look at hands like these with the choreography that they are showing, dancing around this task, and the various fingers performing precise roles in the right rhythm and to the right degree. And so when you look at hands like these, or these are leprosy hands, which are full of stiffnesses and paralysis, you start to realize what I mean by the ineloquent hand and the restoring the vocabulary. And of course, severe congenital defects bring the hand into this category. So this talk really is going to see how the hand is going to achieve what I've briefly shown you. This, of course, is a hand with instability, which is just as debilitating as paralysis. It's useful to start really with forms of grip, and we look at the way the hand adapts to various tasks. But the first and most important concept, of course, is the precision we're considering is all vested in the intrinsics. The upper limb girdle and forearm musculature provide the power, while the intrinsic hand muscles provide the precision. I've fancifully taken this photo to summarize that. And I'd like to introduce you to this concept, which is the difference between centralized and peripheral grip. Okay, so centralized grip is typified by this sort of action. And although it looks like this, the hand is the active participant here. In fact, all the power is being produced by the forearm. And as soon as one grips a tool, a racket, a hammer, a bat, that upper limb becomes racket, becomes hammer. As soon as you grip in this fashion onto any tool, the versatility of the hand is lost. In fact, it's not required, because all of the function is coming from the trunk. In other words, from the central part of the body. The hand and forearm, indeed the arm, behave as a rigid object, while the rest of the body does all the maneuvering. So this is centralized grip. Okay. Peripheral grip is when one devolves all this grip to this sort of task. And in this case, we are using the small interphalangeal joints to provide accuracy rather than power. And you can compare these two if you compare blackboard writing with writing on a desk. The blackboard writing may be very attractive, but is not as accurate as writing on a desk, where your hand is steadied on the surface. In fact, in our profession, when we want to perform something immensely precise, not only do we not need our central muscles, the centralized grip, but it actually is a detriment to the task we're trying to achieve. And therefore we eliminate it by stabilizing our forearm from elbow right to the tip of the little finger, so that we can then use only the delicate and very accurate interphalangeal joints, which are full of proprioception, as we shall see later on the talk. So if we look now at types of grip, the most basic primitive grip is scoop grip. If you gather objects towards you, you are producing scoop grip. Again, the versatility of the hand is not required. And you may think you don't use this very much. Even a digging dog has this, but in fact we do use it when we lift an object like this. This is centralized, of course, because the hand is just the end of the limb, and the power is being produced by the center. But we have thumbs, and therefore this gives us power grip and also hook grip. Again, both of these are immensely powerful, but accuracy is not a feature. Side-to-side grip looks accurate, but actually is not at all versatile. The most specialized side-to-side grip is key grip. And when you think about it, although you're using the tips of fingers or close to the tips, once you clamp onto that object, there's very little you can do. You can perhaps pronate and supinate and move around and write on a blackboard, but you are not making use of the versatility of the intrinsics. If you need something a bit more accurate and controllable, then you are going to devolve to these joints, as I have said. And the most accurate grip we have is 3-point grip, chuck grip, tripod grip. It has many names. And this is the most accurate that we have. It's no accident that we use it for writing. All the people listening in here will have not only a very accurate handwriting, some more than others, but certainly very distinctive handwriting. And handwriting is a very good example of what I like to think as the choreography of the hand. Handwriting is a programmed dance across a page. Of course, the hand, as I said at the beginning, has a sensory role, and you're all familiar with the homunculus, which gives every part of the anatomy in proportion, draws it in proportion to the amount of sensory input it's bringing. And you could probably do the same with the hand, where the pulp is absolutely huge compared to the rest of the hand. And this also introduces the concept of the leading and trailing edges to the hand. These are the common points of contact, and analysis of this skin will show it to be over-endowed with sensory end organs. If you compare, for example, the ulnar pulp of the thumb with the radial part of the thumb, there's a huge difference in the sensory end organs. So this concept of leading and trailing edge is truest of the thumb and least true of the index. The index is often involved on both sides. And so when you see this form of grip, which is using the leading edges of thumb, index, and middle finger, a form of three-point grip, you can see in action the leading edges of these fingers. This has enormous reconstructive implications, of course. What you do with a leading edge is not the same as what you do with a trailing edge. So who are the participants that give us this versatility in function? The intrinsic muscles of the hand are so called because they arise and insert in the hand. And so it is all the muscles beyond the wrist crease. And it may surprise some of you to know that there are only 18. This very versatile part of our anatomy has only 18 muscles in it. Remember, the performance also depends on the muscles proximal to it in the forearm. By the way, 18 is variable. Some people will consider that other muscles like palmaris brevis or some aberrant muscles are also included, but by and large, we have 18 muscles in our hands. And the general topography is of 2 hills and the valley. And through the valley, a lot of clockwork, important structures travel, emanating from the carpal tunnel. And already you can see, because of these 2 muscle hills, that the tendency for the hand is to close into flexion. There are 2 columns of muscle that are tending, therefore, to surround an object. And it's not just muscle. Here is a hand denuded of all muscle, indeed also the finger skeleton, but the metacarpal heads naturally assume a curve, as you can see. So they are already trying to curve towards the held object. And this is the basis, of course, around which our fingers then behave. And you can imagine around the world, in various cultures, in various strata of society, how important this cupping of the hands to carry water, rice, whatever, how important that is. It's a very basic element of our activity. And this is further made possible by the fact that the joint at the base of the thumb is the most mobile carpometacarpal joint in our hand. And the next most mobile is the little finger carpometacarpal joint, and the ring finger is also moderately mobile. The index and middle metacarpal are fixed. They are virtually welded to the carpus. But the border digits are mobile, which means that they can further curve in to surround an object. In fact, you can consider that virtually the whole body is designed to be in flexion, starting from this posture in the womb to other activities that we may care to indulge in. If we want to lift the box, it's very natural for us to reach for it in flexion using the actions forward rather than backwards. It's possible, of course, to lift backwards, as you can see in this photo, but it's certainly nowhere as versatile, and we were clearly not designed to tend to that side rather than in flexion. We are designed to be in flexion, mainly because of these 2 columns of muscle. And you only have to see a hand that is paralyzed. This is a median and ulnar paralysis, where this natural curvature is lost, to realize how abnormal that hand looks. And this has implications, as we shall see further down this talk, on the way the thumb dialogues with the rest of the fingers. Okay, the thumb is brought into a position where it can, to most benefit, interact with the other fingers. The intrinsics also give the hand its characteristic shape. Those of you who've worked with me know that I sketch all my operation notes, and the first beginning, if you sketch a palm, is to sketch a square, as you can see here. With paralyzed and wasted hands, I noticed that the palm is rectangular, as you can see here. And when you think about it, it's because the muscle is wasted on one side and on the other, but the length is a skeleton, and that cannot vary. And therefore, you get a rectangular palm. The other side also gives you a characteristic shape. Again, most people will see this hand and will realize something is wrong. Those of you who know a bit of hand anatomy will say, this looks empty, it's hollow. The posture of the hand is also depending on muscle bulk and tone. Again, this is a median and ulnar paralysis in the hand in leprosy. And you can see this artificial posture that is consequent on the wasting. There's severe wasting in the thenar eminence, as you can see here. The intrinsics are also responsible for stability, and we shall deal with that in the second talk, which is on tendon transfers. If you all know that stability in any joint is dependent on the shape of the joint, on the ligaments around it, but more and more one realizes how much muscle plays a part in making that joint stable. In fact, in this case, where you have a wasted thenar eminence, if you try to grip an object, the thumb just buckles backwards. So if we now go further into the intrinsics, and we can see how they can perform tasks like this, ones of accuracy, not just in orientation in space, as in threading a needle, but also in isometric power and grip. Let's look at various groups of muscles, starting with the thenar muscles. You all know that there are three thenar muscles: flexor brevis, abductor pollicis brevis, opponens pollicis. Of these three, the most important, and again, remember how I defined important, is the abductor pollicis brevis, which brings the thumb away from the palm at right angles to the palm. And it inserts into the extensor hood, and therefore with the adductor pollicis helps stabilize the long extensor in exactly the same way as the interossei helps stabilize the long extensors and the long digits. You might think that the antagonist of abductor pollicis brevis would be the adductor from the name, but actually it isn't. If you consider that the abductor pollicis brevis is producing antipulsion, the muscle that's producing retropulsion is the extensor pollicis longus. So the antagonist of the APB is the EPL, not the adductor pollicis, which is going off in a completely different plane. The flexor pollicis brevis is a muscle that lends itself to others and supplements others, as we shall see. One of its main functions is to stabilize the MCP joint in exactly the same way as the interossei stabilize the proximal phalanx and the MP joint of the long digits. And this brings me to the sesamoids. Let's look at how sesamoids work and why we have them. Here's a charming little drawing by Rembrandt, a red chalk drawing, and I've used it to illustrate. Imagine this man is trying to pull up this flagpole using a rope. If he does it in this way, the vector for lifting the flagpole is going to be very small, while that along the ground is going to be very large. But if he introduces a pulley, he is going to increase his mechanical advantage, and therefore the vector which is raising that pole is going to be a lot bigger than that along the ground. And also remember that you only have to lift that pole a few inches, and then your mechanical advantage extrapolates and increases as you go higher and higher. And this is exactly how the sesamoids work and why they are there. They push the axis, the moment of the tendon forward, and therefore increase its moment arm. Okay, so the flexor pollicis brevis goes over the radial sesamoid, and because it's coming along the line of the metacarpal, it has a poor mechanical advantage, just like the first man pulling the flagpole. And by changing the direction here, the sesamoid is going to increase the mechanical advantage. I can illustrate this differently in a cross section here. Through the base of the proximal phalanx, you can see how the axis, the moment arm of the flexor pollicis brevis increases and therefore makes it more effective. And that gives the flexor pollicis brevis an important role in stabilizing the MP joint and stopping the buckling I showed you earlier when one grips. The flexor brevis also lends itself to supplement the abductor pollicis brevis. The part of FPB, which is supplied by the median nerve, works with abductor pollicis brevis. The part which is supplied by the ulnar nerve will work with adductor pollicis and supplement that, because it does have an adduction action. And to complete the trio, it also works with opponens pollicis. And so there are three elements to flexor pollicis brevis. And remember, as we move on with this talk and we discuss proprioception, because it acts in these various planes, the flexor pollicis brevis is a very important proprioceptor to the thumb. It's relaying back a lot of information. The opponens is a curious little muscle. It invests the metacarpal, arises from almost the entire shaft. And the characteristic of this muscle is that it has a huge variation in fiber length, the shortest being around 15 millimeters and the longest being about 36 millimeters. And if you compare this with pronator quadratus, which has fibers very much of the same order, it may well be that the different length of muscle fibers mean that part of it is always active in any part of the opposition cycle. It's a possibility, it's speculation. Another idea of the opponens pollicis, I think, is slightly tenuous, is the fact that it pushes the abductor pollicis brevis away and increases its moment arm, much like a sesamoid would do when it wants to start abduction. The next muscle would be the adductor pollicis, a very powerful muscle. I consider the adductor pollicis, which you can just about see here from the dorsum, and the first dorsum interosseus, like the pectoralis major and latissimus dorsi of the thumb. They fulfill the same role as those two big muscles in the shoulder girdle will do in the thumb. The adductor pollicis will insert into the extensor hood here in symmetry with the abductor pollicis brevis. And through it, sorry, let's go back, and through it will influence all three joints. So through that hood, because through the long extensor will tense up the interphalangeal joint. It will stabilize and slightly flex the MP joint. But its main lever arm is on the carpometacarpal joint. You can see the mechanical advantage it has and why I call it the pectoralis major of the thumb, really. It's a very powerful adductor of the thumb. You can see more of it here on the palmar side, but some of it is still covered by the flexor mechanism of the index and middle, because it is coming from the third metacarpal and the carpus, as you can see here. It comes in two heads, and they converge onto the extensor hood as I've shown. Now, if you were going to produce an adductor, you would imagine that it would be to the first port of call. So it would be to the metacarpal of the index, like the first dorsal interosseus. But in fact, because the thumb is going to come across, if you did that, you would have only a very small sphere of influence. It wouldn't reach over to the ulnar side. And so the origin comes from the middle finger metacarpal, which gives this a much bigger sphere. And therefore the thumb is now in the axis of the hand. Remember, the axis of the hand is the middle finger. And this is further helped. It brings more into range when you consider, as we said earlier, that the base of the little finger metacarpal is mobile and therefore can approach the sphere of influence of the adductor pollicis. And so from this brief summary, you can see that opposition, which is, you can see on the bottom left here, a combination, a sequence of abduction, flexion, adduction, and pronation, starts median and ends ulnar. So the abductor pollicis brevis will bring the thumb away, and the adductor will then bring it to dialogue with the fingers. The adductor pollicis, I've taken all the flexor mechanism away here. You can see all of its extent, and you can see here the deep palmar arch and the motor branch of the ulnar nerve coming between the two heads. It lies in the deepest reaches of the hand. It lies against the metacarpal shafts and then passes to the ulnar hood of the thumb. And so having done both sides of the hood now, we can see how the long extensor is stabilized between the adductor pollicis, which you can see here, and the abductor pollicis brevis. And here's another view to show you how symmetrical is this mechanism, identical to the long digits. Okay, one final thing about the adductor pollicis, this powerful muscle converges onto the hood, as we have said. On the other side, the flexor pollicis brevis and the abductor pollicis brevis also converge, which means that between them, they form a very powerful stabilizer of the metacarpophalangeal joint. I'll emphasize this and crystallize it in your mind by taking everything else away. You can see how this sling between the powerful adductor pollicis and the flexor brevis and abductor brevis are going to stabilize the MP joint, and why they allow the MP joint to buckle back when they are missing, like this. So the intrinsic minus thumb, remember throughout that the thumb mechanism for stabilizing the MP joint is identical to the long digits. The short muscles at the base, at the level of the metacarpal, stabilize the MP joint. And so you will see patients who try to grab an object like this, who have a wasted thenar eminence, will collapse their MP joints dorsally. And if you observe them carefully when they hold an object, they will tend to hold it as I have shown on the left. This is my hand posing here, in order for the object itself to provide stability and to prevent the joint buckling forwards, as it does on the right, as you can see here. It's also, before we leave this, to remind you, and we'll talk about this next week, that when you replace adductor pollicis by tendon transfer, you need to go beyond the axis of the joint in order to provide this stabilizing influence that I've just described. Moving on to the first dorsal interosseous now, this is the latissimus dorsi to the pectoralis. The first dorsal interosseous is, as measured by Brand in his tension fraction scales, the most powerful weight for weight, most powerful muscle beyond the elbow. So in other words, considering its volume, the power it generates, it is the most powerful. That means it's more powerful in proportion to its volume, say, than the flexor pollicis longus. It's an interesting muscle. It provides very strong key pinch, as you can see. And one of the keys to its function, and therefore why we miss it when it goes wrong, is its old name. The old anatomists used to call it abductor indicis. And it does stabilize the MP joint of the thumb. Remember that if you are grabbing something hard like this, there's a very long lever that is going to tend to move the index away, and the first dorsal interosseous will resist this. In fact, those who have a paralyzed or weak or atrophied first dorsal interosseous will recruit the other digits to help stabilize the index. I'm sure a lot of you will have seen, will be very familiar sight there, where you see elderly patients who have a wasted first dorsal interosseous from CMC joint arthritis. They will recruit the other fingers to stabilize the index so it doesn't give way. And the sharp-eyed amongst you, the observant amongst you, will also have noticed that the problem is made worse here because she's subluxed her extensor tendon, which is producing an ulnar translation to this proximal phalanx. First dorsal interosseous is also a rather interesting, in fact, unique muscle. It doesn't just arise from the two metacarpals, it also arises from the intermetacarpal ligament, which I've drawn here, which means that when it contracts, it lifts the intermetacarpal ligament and brings the bases of the two metacarpals together. The consequence of this is that it reduces the pressure in the joint. It produces a negative pressure in the joint, which is quite an unusual function for any muscle action, to produce negative pressure in a joint. Let's look at the implications of this. As we shall see a bit further on in a bit more detail, there is a tendency for the base of the thumb metacarpal to slide down the slope of the trapezium. And the first dorsal interosseous protects this. Let's look and compare the adductor pollicis with the first dorsal interosseous. I'm using this drawing. The adductor pollicis, when it contracts, is going to pull the metacarpal head towards it. and therefore it's going to make the base of the metacarpal go dorsally and in a radial direction, which means that in this left hand with this action, it's going to make the metacarpal go counterclockwise. If we now look at the first dorsal interosseous, it's going to pull on the base of the metacarpal and therefore make the metacarpal rotate in this hand clockwise. So you can see that the two cancel each other out. They produce between them very powerful adduction, but it's a stable adduction, a bit like the short muscles around the shoulder will stabilize the humeral head when you abduct, for example. And so you can start to work out really what the stabilizing forces are for when you grip something hard between thumb and index. You can see that here the adductor and the first dorsal interosseous are both working together to stabilize this index. And of course, it also depends on the integrity of the collateral ligaments of the PIP joint. And you could go further and consider the interossei doing exactly the same thing with this other finger and stabilizing and lifting, supporting the weight of that mug. Let's look at a bit more detail at the thumb now. The thumb, we're always told, has a saddle joint at the base. But Kapanji observed, as did Kuczynski, that if this were a saddle, it would be a saddle for a scoliotic horse. And the reason they said this is because of the unequal size of the radial and ulnar condyle to the trapezium and indeed to the metacarpal head. This means that if you abduct this thumb, it will tend to rotate into pronation because the axes of the joints spiral as you go up the joints. Okay, so the thumb corkscrews its way around into pronation. Nothing to do with muscle, purely as a result of the shape of the joint. The radial condyle pushes the radial base of the next bone along further than the ulnar condyle will. Okay, these are the different axes of the joint, as you can see. And the pronation happens around the axis of the beak ligament. Here's the beak ligament dissected out, and this is how the pronation is going to happen. Again, remember, it's nothing to do with muscle. So here's a short film. This is my hand abducting the thumb precisely in the axis of the index finger. Observe what happens to the nail. Okay, so that thumb with no extra muscle action is pronating as a consequence of the bone, the asymmetrical bone shape I showed you. And so at the start, that nail was virtually vertical, and at the end, it had come round by about 45 degrees. And this is a very important function, which is not dependent on muscle, as we've seen. Why is the thumb on a slope, and why is it at this angle? Okay, so the thumb is pointing away, does not lie in line with the other digits. Well, remember that the thumb needs to dialogue and interact with the other digits. And if it were on the same plane, it would be like these five beauties here. If they wanted to talk to each other, they'd have to do it to the side of their mouth like this. While the hand is organized more like this, where the thumb is able to interact with all the other digits virtually equally. In order to achieve this, it has to be on a slope, sloping away from the other digits, which immediately introduces a problem because there is, as we've just said, a tendency for the base of the metacarpal to slide down and to wear that joint asymmetrically. And it's no coincidence that the strongest ligament at the CMC joint of the thumb is the volar beak ligament, which is, like these men, stopping that metacarpal sliding downhill. And we all know the consequences of this. The CMC joint of the thumb is the commonest worn joint in the body, more common than the hip or the knee. Our thumbs can oppose, and this vastly increases the versatility of our hand. You only have to see the way a hand without a thumb works and how it then works once you policize. One of the most satisfying operations that we do as hand surgeons to polysize an index and create a thumb and take the scale of function of that hand up enormously. We are not unique. The chimp family, the chimpanzee family, has an opposable thumb, as you can see from the creases here and from the thenar eminence. The big difference between us and the chimps is the relative length between thumb and long digits. Okay, if you compare this hand of a chimpanzee, clearly designed to hang from branches, while with our hand, and if you see the skeleton here, the long digits are vastly longer than the thumb, which means that the tips are out of reach of the thumb. And in fact, it's not a function that the chimp regularly performs anyway. Its main interest and key to survival is to have powerful long digits to hang and swing from branches. So when you see a member of the chimp family, an orangutan baby, hanging, it's hardly using its thumb. It's not using its thumb. In fact, it's a passenger, as you can see, hanging loose. So the fact that we have a thumb and we have all of these fine and sensitive muscles to control it and the other digits, as we shall see, the neighboring digits, gives us this precise grip of 3 points. The hand that is not able to oppose the thumb is merely able, if you invite it to oppose, the thumb is merely able to travel along the plane of the palm. I've got a more brief film here. This girl is being asked to touch pulp of thumb to pulp of little finger, like that. And as you can see, the plane of the nail, it's always the key, doesn't change.
Do it again.
You see, the plane of the nail remains virtually vertical in that film. It can be a congenital defect, of course. This is a Blouth 1 with a missing thenar eminence. And as this child develops, you can see this is a Blouth 2. The consequence of not being able to abduct that thumb means that the metacarpal of the thumb and the first doesn't move away from the metacarpal from the index. And again, you can see here that if you invite this person to oppose, the plane of the nail tells you the whole story. That is virtually vertical, and that is facing us. So this one is merely flexing, not opposing. And as I said, the two metacarpals of the thumb and the index don't move apart. The first web space contracts. And as this child develops, in this case into puberty, the stress of using the thumb without being able to abduct the metacarpal will lengthen and make lax the ulnar collateral ligament. And we shall see methods of reconstructing this in the second lecture. Let's move on to the interossei now. You do know that the interossei are well named. They invest the metacarpals. They are between the bones. The axis of the interossei, as always in the hand, is the middle finger. It's very difficult to show even with this extensive dissection, which has removed all the neurovascular structures because there's so much else in the way. But if you remove the flexor apparatus and the hypothenar and thenar muscles, you can see the interossei investing the metacarpals. And they're often grouped with the lumbricals, but we shall see some important differences between the two functions later on in this talk. We are always taught that the main function of the interossei is abduction and adduction. I would put to you that this is the least important. And again, remember how I'm using the word important. The second most important function, particularly of the lumbricals, is the coordination of flexor and extensor apparatus. And we shall see why this is crucial. But by far the most vital function that the lumbricals and interossei, particularly the interossei, perform is the stabilization of the MP joint. Once again, it's exactly like in the thumb. That metacarpophalangeal joint must be prevented from buckling backwards. To this, you can add the stabilizing influence of the thenar and hypothenar muscles, as we've seen earlier on the thenar muscles. Okay, so this whole population of muscles, their main function in motor sense is to stabilize the MP joints. Let's consider abduction, adduction. I don't want to dismiss it. It's a very important function. Why is it possible to start off with? It's possible because of the shape of the metacarpal head. The metacarpal head is cam or egg shaped, as you can see here, which means that the axis along the finger is shorter than the one into the palm. So as you can see here in extension, the collateral ligament here will go lax, while when you flex fully, those collateral ligaments will tense up. I've got a brief film here to show you this. So here's a dissection where you can see in full extension that metacarpophalangeal joint is entirely unstable. You're able to abduct and adduct. As soon as you flex it, it goes rigid, okay? You cannot distract it. And this is the way to test for a torn collateral ligament, of course. You test it in flexion because that's when they're all tense. Why is this important? What is its purpose? Well, when you reach for an object in midair, you don't need stability. You need to be able to open, to surround that object. So abduction and adduction are very important to you. When you grip the object, now you need all the stability you can afford, and therefore those joints lock, and they lock around the object that you are holding. What is the action of interossei and lumbricals? We'll keep them together for the moment. Well, they will flex the MP joint and they will extend the IP joints. Okay, the interossei are more powerful flexors of the MP joint, while the lumbrical mainly acts on the PIP and the DIP joint. So given these axes of action, when you have excessive activity by the interossei and lumbricals, it's a bit of a misnomer to call them intrinsics because the intrinsics include the thenar and the hypothenar, but let's stick with that for the moment. When you have an excess of action or scarring or contracture, then you get the position of intrinsic plus. So if you pull, in this case, on the lumbrical, you will get a rigid extension of the PIP and the DIP joints. Here's a film to help illustrate it. Let's go back to that. Okay, so I'm pulling on the lumbrical tendon there, and you can see how the PIP and the DIP tense up. Okay, this is the position of intrinsic plus, as you can see. Okay, so we're flexing the MP joints and extending the PIP joints. And we test for this with the intrinsic tightness test. If we suspect intrinsic tightness, we extend the MP joint, and then we test for tension resistance to flexion of the PIP joint. So in this case, we are putting the interossei and the lumbrical on the stretch to maximize their pull, and then we test for the tension. And the second part of the test, we flex the MP joint, thereby relaxing these two muscles as far as is possible, and then test the resistance to flexion of the PIP joint again. And you can compare the two, and you can almost quantify how much intrinsic tightness there is. The more important, the more significant player in this scenario is the lumbrical. For various reasons, including the distal insertion. And so it inserts, as you can see, by this string-like tendon almost at the PIP joint. And if you want to do an intrinsic release, this would be your first port of call. The lumbricals, incidentally, are weak in motor power, but when they cause mischief, they cause more mischief than the interossei for this reason. And I will tell you why I say that. When we do an intrinsic release, we excise Littler's triangle here. And personally, in my experience, over 90% of cases, that is enough to get a much more relaxed Finocchietto test, which is the one I showed you. So in other words, the lumbrical was the main player in that intrinsic tightness. Of course, you can carry on if it's not enough, and I'll show you the extensor mechanism now here to emphasize this point. You can pull again on the lumbrical there, and remember the lumbrical streams into the long extensor. That's a triangle which you would excise. Here's the interosseous inserting into bone as well as the sagittal bands, and then the further fibers stream into the extensor mechanism, as you can see on the radial side, and on the ulnar side. Here I'm lifting up the palmar interosseous, which will adduct the finger, and between them they will stabilize the extensor hood here. They will create the extensor hood to stabilize the long extensor, which then of course carries on, gives off the central slip, and then the lateral bands into which these muscles I've been describing will insert, and they carry on almost as the extension of the interossei and the lumbrical. Okay, so if it's not enough to excise the triangle, and I will stress that in the majority it is enough to excise the littler triangle on the radial side, interrupting the line of lumbrical, then you carry on with the same incision, of course, because it's so accessible, and do the triangle on the other side. But it's often not necessary. What causes intrinsic tightness? Well, I think it happens very often when we miss compartment syndrome in the palm, in the hand. Everyone knows about compartment syndrome in the forearm, and most people will look for it. And you know, every junior will know that if you're suspecting compartment syndrome in the flexor compartment, you put it gently on the stretch, and that causes a disproportionate pain. Well, I would put to you that we should do this more often and test the compartment syndrome in the hand. And this would be the way to do it, by putting those two muscles that I've been describing on the stretch. All too often we ascribe a stiff hand to the original pathology, say metacarpal fractures, but actually that hand has suffered ischemia in the interossei particularly, and caused intrinsic tightness. What about the opposite, intrinsic minus? Well, we said that these muscles that we've been talking about will flex the MP, will extend the IP joints, and therefore the opposite happens when these muscles are paralyzed. And you get the characteristic posture of intrinsic minus. Most people will call this a claw hand, which I think misleads into where the real pathology is, because it focuses on the flexion of the fingers. But actually the crucial event here is the hyperextension instability of the MP joint. If you can correct that, you probably correct the entire deformity and instability, as we shall see, particularly in the next lecture next week. So here's a mild intrinsic minus hand. You see very severe ones in Nepal with leprosy patients where I go. These are very mild because they're caught relatively earlier in our societies. And if you were to stabilize the MP joint using your examining hand, like this, which is the Bouvier test, then you ask the patient to straighten the finger, they are able to do so. If you can compare, if I go back here, look at the very faint creases on the back of the PIP joint here, and look at the marked creases as they are forcefully extending the PIP joint. So this would be a positive Bouvier test. And it tells you that what you are doing here is the lumbricals and interossei are paralyzed, but the instability that the paralysis has caused has been eliminated by your examining hand. And the long extensors are then able to extend the digit. And this is the rationale for those hand therapists who are looking in on this, of this so-called ulnar claw splint. Again, I don't like the name. It stabilizes the MP joint so that you're able to straighten and open your fingers and close them. Let's look at some film of the claw hand. And you can see here how when you invite somebody to close their fingers, how they roll up from the tip, as I will show you in a minute. Okay, so this is a Bouvier test on this hand, and you can see it's positive for the middle and ring fingers. In other words, there is an intact extensor mechanism there, but it's negative for the little finger because the central slip here is attenuated. And so these fingers will need different treatments, as we shall see again next week. Okay, let's move on. So that those two digits have got a long extensor apparatus intact, and what we'll see next week, the lasso operation is indicated, while in this case, the central slip and extensor are attenuated, and you need to think a bit further and restore active extension to that PIP joint, as well as stabilizing the MP joint. All this will be dealt with next week. So let's consider the lumbricals now as motors. Okay, you all know how they arise from the flexor tendon. They're quite unusual, if not unique, by arising in one tendon and inserting into another tendon. And for this reason, their insertion and origin are very fluid and they have a long excursion. Brand measured the tension fractions of all the muscles below the elbow and expressed the power they generated as a proportion in relation to their volume. And therefore, every muscle got a tension fraction, as he christened it. Let's not go into that. Let's consider the lumbricals as a group compared with the interossei as a group, and you can see the totals down here, which give you this, that the power of the lumbricals as a group is only approximately 8% of the interossei as a group. So they are weak motors, okay? Let's look a bit at their anatomy here. You know that the biggest and most constant lumbrical is the one on the index, and it travels to the extensor hood, which you can actually access through the palmar access. There is an incidence of normal anatomy. The index and the middle are the most constant, and there is a reason for this, as we shall see, while the ring and the little finger are not as constant in their anatomy, and indeed the little finger lumbrical is absent in just over 5%. Let's look at the function of the lumbrical now. I said at the very beginning of this section, I said that there is a coordination between flexor and extensor tendons. Why is this important? What does it contribute to the language of the hand? Well, if we look at a finger in a puppet and we attach a piece of string to it and pull, what's going to happen? Here's a model I made for you here with a piece of string. And if we pull on this piece of string, the first thing that will happen is a full flexion of the DIP joint. The next thing will be a full flexion of the PIP joint, and finally a full flexion of the MP joint. And precisely the opposite happens, the opposite sequence happens if we pull on an extensor, full extension of the DIP, full extension of the PIP, full extension of the metacarpal. And this is the way a puppet's hand will work. In other words, it will curl up from the tip and the distal joints are favored. They will go and act before the proximal joints. So the sequence of contracture, of flexion, is going to be 1, 2, 3, distal, proximal, and metacarpal, phalangeal. So you ask a patient with intrinsic minus like this to make a fist, and they manage to make a fist. And you think, well, what's the fuss? They can make a fist. Well, the crucial difference is that these fingers are behaving like this toy trumpet. They are curling in from the tip. I'll show you some film of this. Okay, so this person is being asked simply to flex, and you can see how he starts at the tip and then the fingers curl in. Here's another one, again, very consistent behavior. The tip comes in first, the end joints come in first. In fact, they never quite straighten, and then the base. And perhaps the best one of all is this one. You can see how you curl in from the tip. What is the significance? Why does this harm the function and impede the hand? This is from Brand's book. The normal hand will surround an object in a very even way because those fingers close in synchrony. While in this hand, which is paralyzed, which has an ulnar paralysis, the tips come in too soon, and therefore they hit the object and you never quite get into contact with the rest of the hand, the rest of the fingers. When I first started my leprosy work, I tried this out. I gave my patients a cylinder with poster color on it, and I asked them to grab it. And this was a very typical imprint map that I got. You can see the contact as described in that diagram. And the significance of this is that when they reach for an object, this is what happens. They are unable to surround it. And therefore, it's very important to achieve synchronous flexion of all three joints. What does this require? it requires us to slow down the distal joints and favor the proximal ones. And this is exactly what the lumbrical does, even as a passive passenger. As the flexor profundus contracts, it sends off the lumbrical to the dorsum, which at the same time slows down flexion on the distal joints. In fact, it slows down the distal joint more than the proximal interphalangeal joint. So this is called the extension brake. Okay, and that achieves, it's perfectly calibrated to achieve a synchronous closure of the fingers. I'm going to go off-piste here a bit and describe other mechanisms which achieve this same function. In other words, slowing down the distal joint. For instance, the size of the metacarpal head, of the proximal phalanx head and of the middle phalanx head gives you a gradation in moment arms, which means that the flexor tendon has a bigger moment arm proximally than it does distally, and therefore is going to favor the proximal joints. The other very elegant mechanism, which is again not muscular, is one described by Toubiana, and this depends on the oblique retinacular ligament. You can see that when this flexor contracts, the oblique retinacular ligament is going to go tense, and therefore as the DIP joint flexes, the PIP joint is going to start flexing because the oblique retinacular ligament of Landsmeer is pulling it with it. As these joints flex, that ligament relaxes. And what happens next is that the extensor hood migrates distally, and by migrating distally, it's now going to make the flexion of the metacarpophalangeal joint even more efficient because the hood has a better mechanical advantage on it. Okay, here it is pulling on a more distal point in the proximal phalanx. And so this whole sequence like this, oblique retinacular ligament, then it relaxes, and then it pulls the hood distally, which was described by Toubiana in this publication, will help what I've just been saying. These are just three mechanisms. There are others, in fact, but the lumbricals is the most elegant. Another function of the lumbrical you can see in other primates. The gorilla walks so-called knuckle walking. Okay, and in order to achieve this, it hyperextends its MP joints and flexes the PIP joints. Okay, and so in this position, the interossei and especially the lumbrical will prevent excessive flexion of the PIP joint, which is essential, therefore, for stability if you're going to walk on your knuckles. The knuckle is a bit of a misnomer. We take the knuckles to mean the metacarpophalangeal joint. In fact, in this case, the metacarpophalangeal joint is hyperextended to make the interossei and the lumbricals even more efficient. As you know, when you stretch a muscle, it becomes even more efficient. And so here is a different function, and they're much, much more powerful than in man for this reason in the orangutan and in the gorilla. The lumbrical is a weak flexor of the MCP joint. And the reason it's weak is, although it's got a good moment arm, remember it's the only muscle that goes volar to the intermetacarpal ligament, the others are all dorsal. If it contracts, any pull proximally that it achieves is balanced by a pull distally of the flexor from which it arises. And so Brand in his book rather amusingly describes it as the son riding on the father's shoulders can offer to carry the suitcases, but the father won't notice any relief on his knees because the same weight is being carried. And the same way, the lumbrical is helping the flexor pollicis, flexor digitorum profundus, but actually not helping because it's pulling in the other direction at the same time. And one of the demonstrations of how weak it is will come with the latent claw test. In terms of motor function, the lumbrical is to be considered mainly an extensor of the IP joint. Here is the latent claw test. This is a person with an ulnar claw paralysis, ulnar paralysis, being asked to assume the intrinsic plus position, and then the finger is challenged. the person is able to do this. Remember, all of the interossei are paralyzed and the ulnar lumbricals are paralyzed. The only reason these two fingers are not in a claw posture is because the lumbricals are preventing it. But if you challenge them, this is what happens. They collapse. So you will see that they're not able to maintain that position, and sooner or later they will fail. Far more importantly, as a function, is the lumbrical as a sensory organ. Remember that muscles are very important sensory organs, and their importance is proportional to the number of muscle spindle sensory receptors. And these detect both stretch and speed of stretch. Here's one of 2 or 3 very few text slides. The spindle-rich muscles in the body are the ones that you'd expect. The extraocular muscles, the muscles of the tongue, the muscles of the jaw, the masseter, and the lumbricals. Okay, these are all muscles that need to be very precise, very fast, very accurate. And in the upper extremity, if you look at all the muscles in the upper extremity, the lumbricals have got the smallest cross-sectional area, but they have the highest density of muscle spindles. And not only that, but they have the highest number of intrafusal fibers per spindle. So in other words, each spindle can transmit more information and there are more of them. There's a high density of lumbricals in mammals generally, and man and the chimpanzee have got the highest frequency, and it's no accident that these are the 2 creatures who manipulate with their hands. In the human, and we shall see why, the highest density is in the index and middle. So if you compare, for example, the cat that does not maneuver with any digits, it's got very few total in its paw, 27. The chimp has 112 and man has 138 spindles in all the lumbricals, index to little finger. And in this role, the lumbrical is very well placed to transmit information back because of its relatively huge excursion. Remember, for a short muscle, its origin moves by 3.5 centimeters and its insertion moves by 1.75. So the total excursion is 2.75. That's a lot of excursion. Some lumbricals are hardly longer than that, which means that almost 100% of their length is their excursion. And so the more excursion you have, the longer fibers you have in the muscle, and the lumbrical fibers are from beginning to end, from proximal to distal, the more efficient you become as a sensory organ. And therefore, that lumbrical becomes crucial in achieving tasks like this, which we said are very characteristics in individual, or tasks like this of great accuracy. And they come into play particularly in the index and middle because of this accurate action. So considering this most accurate of grip, the tripod grip, the leading edges, the leading surfaces of these 3 digits are highly endowed with sensory end organs, and the lumbricals are also the richest in spindles. And therefore the function of the lumbricals in this regard, in the sensory side, proprioception is vastly more crucial than the motor. Of course, remember what we said about synchronizing the 3 joints in the digit, and we've moved on from there. An interesting concept is that of parallel muscle combinations, which was enunciated by Peck in 1984. And this is the idea that big, powerful muscles have got a companion that is smaller and richly endowed in sensory qualities. And so you can imagine that the lumbrical is a better proprioceptor, very efficient gatherer of information by comparison with its much larger interosseous companion. So this would be a parallel combination, and possibly even with a long flexor. So in other words, because it's influenced by the action of the flexor, it sends back relay information that is going to modulate the function of both the interossei and the long flexor. And this is the publication. Those of you who will look at this talk again can note it down. later. It's a very interesting and clever concept. And so this coordination of flexor and extensor mechanism has got huge implications, both in the efficient performance of the closure of fingers and in the relay back of information from the PIP joints. Remember also that these three crucial digits are all supplied by the median nerve. And if you then consider that the lumbricals are proprioceptive organs primarily, I always fancy that if you were to produce a spy camera, provide a spy camera like a CCTV in the hand, you should put it in a lumbrical, because the lumbrical knows everything that's going on in the neighborhood. In fact, the lumbrical is like the neighbor who's constantly watching out, a nosy park over neighbor. So if you put all this together now, the median nerve territory in the hand is immensely accurate in its form of grip, immensely endowed with sensory skin, and also with proprioception from all these small muscles that we've been describing. My final section here is a brief one, and I owe it to my very good friend and colleague, Wim Brandsma, who may be listening to this lecture. He and I work regularly in Nepal. And he pointed out, and I need you to keep this in mind, that no matter what action in the hand, however simple, it depends on the coordination and cooperation of many other muscles in the hand. So when I've said abductor pollicis brevis, abducts the thumb, etc., these are never, ever isolated actions. And here is a sequence devised by Wim to prove that. Let's take the simplest action that we can imagine, abduction of the little finger. What causes this? Abductor digiti minimi. Where does it come from? It comes from the pisiform. So in order to make that contracture more efficient, we need to stabilize the pisiform. How do we do this? We contract our flexor carpi ulnaris. But if we did that, our wrist would flex. And so to counteract it, we contract extensor carpi ulnaris. But if we did this, we would ulnar abduct the hand. And so to counteract, flexor carpi radialis comes into play, but that would cause flexion of the wrist. And so the three dorsal muscles on the radial side, ECRL, ECRB, abductor pollicis longus, come into play. Which means that the simple action, abduction of the little finger, needs the cooperation of 8 carpal bones, 4 metacarpals, and 6 extrinsic tendons. In fact, Wim has, again, cleverly devised this as a test for de Quervain's. If you resist abduction of the little finger, a tender and inflamed de Quervain's, tenosynovitis, will be painful and is much kinder than a Finkelstein test. Finally, some of the rather lovely photos you've seen come from this book, and I need to acknowledge it. The photographer is Basil Powell, and clearly this is copyright, so I want to acknowledge that some of the nicer photos in this book, in this lecture, have come from this book. The drawings and paintings are all mine, and they're available for you to have, and that is the end of the lecture.